Our speaker is started out in electrical engineering, as did I. And interestingly enough, we both saw the light. We went then into physics. But Jim's early education was in Taiwan. He got his bachelor's at Tokyo University, his master's in National Chiao Tung University, both in Taiwan. And then he got his PhD at the University of North Carolina, Chapel Hill. That was in physics. He's been a physics instructor at National Chiao Tung University in Taiwan, did a postdoc at UNC Chapel Hill. He worked at Wright-Patterson Air Force Base. It'd be interesting to know what you did there sometime.
This is aerospace battery research. Aerospace
battery
yeah.
research. Mm-hmm. We have another member who's very heavily involved in battery research. He's not here tonight. His name is John Bates. He was at Orion at the same time.
John Bates used to be my boss.
Oh, really? Really? Okay.
So I was in his group for about 12 years.
Okay. So he's been at Oak Ridge for about 20 years, something like that. And he's now an adjunct at Pellissippi. So very active. And now that he has some time, he's working on his development of ideas about the Big Bang Theory. This is not the TV show, which is great, but the other Big Bang Theory. So very nice to have you.
Thank you, David. Thank you. Some of you probably know me. I have been working at my wife's restaurant for the last 40 years. So that's another work experience. What I'm going to do, I try to review some features related to the observations we're talking about. And also then introduce the infinite non-expanding universe, demonstrate it can explain the same observations. The two main observations I am referring to, one is a distance versus redshift observation, like a mu versus z. And I think that's the most important observation related to the universe. The other one is the existence of cosmic microwave background and how it get the black body distribution. The Big Bang, how did it, how it does it, and the alternative, how to get the black body distribution. How do I do this? My talk difference here is I'm using tools, mainly the calculators. The calculator is based on the lambda CDM model, which is a parameterization of Big Bang model. So I'm talking about Big Bang model, but talking about the calculation results, so I can visualize something instead of just equations. And then the lambda CDM, lambda cold dark matter model, including the simplest case, 3 parameters. One is the Einstein's constant lambda, is related to dark energy. 2, cold dark matter and ordinary matter. And the third one is radiation related to photons and neutrinos. Please come in. So let me explain a little bit of lambda CDM. So just look through this. I don't understand what they are talking about, but that's what it's all about, the model. So it's related to Einstein field equation, and assume the universe is I'm sorry. Assume universe homogeneous and isotropic, and use this metric and then describe the observable universe after the inflation. I'm sorry. So those are just sample equations. I'm not going to use those equations. Basically, the calculator I'm referring to, people integrate those things with those as input parameters. Those 0 means current value. Those numbers like Hubble's constant, omega lambda, omega m, omega r, the current value. And those values determined by like a Planck project and a Kobe project before. So basically, the 0 here is so different. In other words, those numbers we put in, they will calculate the earliest number or future numbers. They are not really constant. It's constant at this time. But then, for instance, lambda, that's density, energy density associated with dark energy. It's a constant energy per unit volume. But if the space is expanding, then that quantity is increasing. And those are the fractions. Say dark energy about 0.7, dark matter and ordinary matter 0.3. Radiation is a very small quantity now. But at the very beginning of the universe, this one dominant, close to 1. This is the percentage. And the matter also was very high. At that time, since the volume is so small, the dark energy total percentage is low. So those things are really changing. That's a wonder of the Big Bang model. So those equations I just show as an example. Okay, there are different online operators. One is University of Chicago, Nathan, and Wright, you're probably familiar with that, UCLA. The one I use most is the Litecoin 8. It's written, and his other people helped him. This jury is the username of Physics Forum, okay? And this one is an Australian site. Those two calculators, including the radiation term. So I like that. Other two calculators ignore, neglect the radiation term because nowadays it's so small. But then this one kept 9 significant digits, this one 15. So if you want to check whether a calculator is working, function properly or not, so those two. I currently, last year or so, Physics Forum, they try to update this program from Litecoin 7 to 8. I found a few glitches, errors, or discrepancies. Now, I don't do programming. I did a programming like a half a century ago. I used Fortran, but now like this program is use Visual Script. They found a person very good at that. So modernize the old program, then fix some of the small errors. Now this one is working properly. The reason I say that is because compared to this calculator, Australian site, those common quantity they calculate, full agreement down to 9 digits, so on and so forth. All right, so much about the calculator. This is an example of this Litecoin 8. It calculates the particle or the size of an observable universe as radius as a function of the cosmic time. So now it's 13.8 giga years. So now it reached like 46.5 GLY, giga light year. So that calculator is so handy. It has chart capability, Then you can calculate 100 entries at one, few seconds. So I like that. I use that a lot. And another one is something called the scale factor in the Big Bang model, which means if you have some distance in space, and this distance keeps stretching with the space expansion. If current value we assume as 1, then early time, the scale factor, can be very small, close to 0. For instance, you heard about the cosmic microwave background. That thing appeared, became free during recombination era. The redshift then is 1090. That means the space is about the 1090 factors smaller than now. So it's very small scale factor then, but now it reach 1. Down the road, it can be increased more than 1. If you have some simple questions, please ask why we can.
The vertical axis is just the size of the universe?
It's a scale factor relative to quantity. Current value is 13.8 is 1. Then other times it become an increase, become more than 1. Then the early time can be smaller than 1. Then during recombination area, all those cosmic microwave photons became free. At that time, it's about 1090 times smaller. And the early time, it could be 10 to the minus 43 times smaller, like a Planck length. So in other words, the universe expand long time, 13.8 billion years ago, from a size, the observable universe, from a size of a point, of a radius of 10 to the, let me see, 10 to the minus 35 meter. That's very small. Current is 10 to the 26 meter, the observable size. So sounds to me, yes, sounds to me is a miracle. Planck length, the smallest possible length. No, nothing smaller than that. So they named Planck. At that time, at the beginning of the universe, like close to the Big Bang, at that time, the observable universe was 10 to the minus 35 meters. No, it's about the Planck length. Yeah,
so they're saying the size of the universe was the Planck length.
Yeah, at that time. Okay. But now
smaller because it's theoretically impossible.
I try to use that as an indication. It's so small, but now it's 10 to the 26, the current radius of observable universe. So to me, it's really mind-boggling. But the Big Bang is a prevailing model, so we can wonder, but we'll see. Vertical is the relative size of the scale factor, huh?
Slide before this, the B, the vertical factor is B.
That's what giga light year, light years, but giga light year. So this one is plot like that. But you see, the output of that calculator is very handy. But sometimes he may plot so many things. Then he put a unit there, and then so on and so forth.
So this line is grown. It's curved, right? It's accelerating. Is that correct?
In a way,
that's
yes.
Not a straight line, is it?
It's not a straight line.
It's curving up.
It's not a straight line.
So in other words, space is expanding faster every year, every minute, right?
not just faster, it's also controlled by those three parameters. A lot of things curve. Okay, so now let's look at this. Those two curves related to the scale vector, scale factor that expand with time, with space, indicate space expansion. And then the size of the observable universe also indicate the same thing. But this one I copied from NASA site. Usually, you know, like start from a very small, then expand. So, you know, and then different time near the current time or this part is dominated by dark energy. Space expand. Then every unit volume expansion, you get extra constant energy. But then there's a dark energy and ordinary energy. The density, the fraction decrease, then dark energy increase, eventually turn all to dark energy. But now let me show you this. See, this is close to the Big Bang. That means the universe was very dense, very compact. But then during the recombination time, suddenly all those photons originally trapped in the proton electron plasma, they become free. They don't interact with hydrogen atoms, for instance. All those photons became free. Then before stars and galaxies formed, then there's a dark ages. Notice here, the first stars formed around 400 billion years. But now this number is relevant here. Recently, James Webb telescope observed galaxies of the order of 200 million years after the Big Bang. So there's a lot of corrections, adjustment to come. You know, maybe the lambda CDM model is not need to change.
Would you say
I think here maybe we should not satisfy saying now we know everything. Probably not that yet. So in other words, this is like a cartoon, say the expansion of space. Look at this curvature thing, not exactly follow the observable universe or scale factor. But you see the evolution of the galaxies, stars, now we reach here. Then also space expansion, the density, for instance, matter density decrease. But because the volume increase, the dark energy part increase. All right. So now let's do some experiment. Suppose we use a telescope and fix at a direction. So one thing we notice, the universe is huge, and what we observe, most of them history. So vast, both in time and space. So let me show you this picture. This is Hubble ultra deep field. That's very early in Big Bang, maybe close to 1 giga-year after Big Bang. And this one, the first deep field from Webb, is a 9.2. So they are not competing. They're just indication. Generally speaking, you know, this covered a width, a time, space wide, maybe like they describe like a straw, then the inside the straw, and so on and so on. So this indication, the universe is really, really big. You know, even you go back to 12.8 giga-years, that far away, you see a lot of galaxies. And then those are homogeneous isotropic. That's, that's the general, large scale general property. Let's look at the redshift spectra things. What we're saying is, suppose you look at a galaxy, we look through a telescope, the spectrum with those lines, originally like this, maybe a nearby galaxy, few 100 million light years away, the spectrum is shifted towards the right side. By the definition, Z is defined like let's look at the 1 plus Z, the observed wavelength and the emitted wavelength. So in this case, it's small quantity. But for my cosmic microwave background, this number is 1090. So the wavelength stretched by more than 1,000 times. So in this kind of things, in astronomy, we use that to discuss things, right? Not we, I mean they. I'm just an amateur. And also the scale scale factor is related to this. If the wavelength photon in space here is 1 and there is 1,000, so that means scale factor also stretched by that amount. Okay. So now I use the light cone A to make a calculation again. Suppose that at a very early time, if something emits a light, and that emitter by now is already moved to a far, far away, maybe close to the edge of the observable universe. But if the emitter is here, then that if the emitted light is emitted here, then the emitter is, then the current that emitter is here. If we emit something right now, then the emitter is right there. So, and that the problem is, not the problem. If we use Z as an indicator, if you say, oh yeah, we observed some recently Webb, the candidate of a galaxy, with a redshift Z equal to 16.7. That means, 16.7. That means correspond to this Z. So the emitter, when the light was emitted around here, very early, close to 200 million years after Big Bang. Then currently, that galaxy is already this far away, 35 gigalight years away. Oh, I'm sorry. So let's talk about the redshift. Now this is the visible spectrum. Microwave around here. So Hubble can analyze wavelengths down to 1.6 micron. This is the 1 micron, down to about maybe around here. And James Webb will go furthermore, analyze the data. So you see, suppose something emitted here and the redshift you analyze here. If the telescope is not equipped to analyze longer wavelengths, then you cannot tell where the galaxy or the light came from. So in other words, James Webb now can observe galaxies or analyze from the spectrum to Z equal to 20. The wavelength stretched to 20 times. So we can analyze infrared. But then Hubble at that time only up to 11. So this is a big improvement. The galaxy I mentioned, I forgot the name, is a candidate, not confirmed yet. is at z equal to 16.7. So the meaning of this is the visible spectrum and redshift and the capability of the telescope. Yeah. Huh?
That's the only electromagnetic spectrum I've ever seen that goes from right to left. All the others go from left to right.
I did a Google search. If I search images, maybe most of them use frequency, but I try to get this one is because it's a wavelength. It's a wavelength.
Increasing wavelength.
Yeah, and yeah, because I'm somewhat familiar with the wavelength concept. You know, microwave wavelength 2 millimeter that peak, but then when the cosmic microwave background first became free, it's in the infrared range around this here. So now those photons wavelengths stretch down to microwave, about 1,000 times longer. So now the CMB black body radiation, we'll talk about that. So I put an arrow here. You see, at the early stage, about 380,000 years after the Big Bang, those photons became free. So now they propagate to here. Now let's do an experiment. Suppose I use a telescope, look at a particular direction. I observe a microwave background photon in microwave range. What can we say about this photon? This photon is one of those photons. It's the original photon, no copy. Then traveled 13.8 billion years to reach us. And that's not the only thing. If I look telescope that direction, another photon free at the same time reach here, every direction. So that's the microwave background. So in other words, we say, oh yeah, like 1 cubic centimeter, there are 410 microwave background photons. It doesn't mean the photons right here. It means a cubic centimeter, so many photons coming from all kind of direction that will pass through this volume. But if we count them instantaneously, there are 410. 410 is a large number. But now the question is, how about the 1 cubic centimeter air? How many molecules in there? 10 to the 20. Photon-wise, it's a big number, 410. But compared to air molecule, it's still a small number. So this, let's look at this. So during the recombination area, when they become neutral hydrogen, and those photons become free everywhere in the universe, uniform, same frequency, the infrared frequency. And now you withdraw, suppose an observer then at the center, if we draw those circles, the thing is like this. For this observer, those photons in the nearby shell will come and pass that observer first. And then next shell, and the next shell, and so on and so forth. But there's a problem. There's a particular shell called the event horizon. Any photons outside the event horizon will never come to us. You know, that this is 13.8 billion years ago, but now they keep coming to us. So I'm sorry. So what I'm saying, 13 billion years ago, a photon in shells like this now reach our location. That's the fancy things about the Big Bang. You know, take a long time. At that time, the distance of those shell, the radius to our position, for around 42 million years. 42 million years. Now it's 13.8 billion years. Now those photons reach us. There's some story inside there, right? How come take those photons 13.8 billion years to travel 42 million years? All right. So photons from nearby shells reach first, and those larger shells follow with the black. So because the plasma and the photons before the recombination area, they thermal equilibrium, so photons in black body distribution. After they're freed, they come from the particular shell to reach us. The space expand, the wavelengths stretch, and someone published a paper. Under that condition, the black body can retain. So that's why Big Bang explained the origin of the microwave background and the black body form. So now it's our responsibility, if you think the universe is infinite, to explain the same thing. Let me show you the the location of a CMB photon near around 380 years after the Big Bang, very close to the observer. But it keeps, instead of coming to the observer, it's moving away. And then someplace it'll come closer toward the Earth. So this is a time, it's not a space. So in other words, if we look at a particular direction, look at that photon. The photon close to us at the beginning and move away and away, but reach some distance, maybe like 6 billion light years, and then it come back. Then finally reach us. We're talking the same direction, just function of time. That's another wonder of the Big Bang model, right? So now let's look at it. Why this photon, instead of traveling directly to the end here, it move away first, come back? It's like this. The recession speed at the photon location. At the very beginning, look, at the very beginning could be so many times the speed of light is carry the photon, even travel toward our direction, but it's carrying it away. But when reach around 4 billion years or so, this recession speed dropped to 1c, and then even less than 1c, and then that photon started to move toward our direction. Again, this is time interval. So now we'll look at the direction, photon nearby, but push that wave and eventually come back. But now let's look at this. Look, the scale factor multiplied by 5, so I can plot it here. So as you can see, during this time photon travels, the scale factor keep increasing. That means the microwave background radiation, those photons, the wavelengths keep stretched by a scale factor. So the redshift is because of recession, because of traveling things, space expanding, so redshift. And now, instead of infrared, now the microwave background has a wavelength of microwave. Now, that's just some information about space telescope. So like Hubble can observe 2Z11, James Webb 20, and for comparison, Moon is only about 1/4 of James Hubble. No, I will show you a next diagram. Now that's Hubble, that's NASA's picture. If this is the Earth, the moon is this far, the James Webb's telescope is here. It's located at a place called the Lagrange point L2. See, that's the sun, the Earth, the moon, and the reason it's located here is a stable orbit. So it easy maintain the orbit, so you don't have to waste energy to keep adjusting the orbit. All right. So now let's talk about the proposed model. So I borrowed this one. So Big Bang is talking about the universe, observable universe keep expanding. Then how about a universe? It's infinite in size and non-expanding. But we assume a photon travel in the photon gas, like microwave background, lose energy to the photon gas. And then we call this, for now we call it CMB drag. And analogies like this. Suppose I have a ball and travel in air. Air has a pressure. The ball suffers a pressure drag. If we drop a ball from high up there, eventually it will settle down to a constant speed, no longer acceleration. That's because the pressure drag. I will explain that a little bit.
CMB stands for.
Huh?
CMB stands for.
I'm sorry. It's a cosmic microwave background.
Thank you.
I'm sorry. Okay, so the photon travel in space, then CMB is everywhere in space, 410 per cubic centimeter. First thing is, photon will lose some energy to the CMB, the cosmic microwave background. And not only that, if a beam of photon coming to us carry the picture of a galaxy, the intensity will attenuate just like anything because of the interaction. Okay, so the CMB drag. If suppose an object moving in CMB with some velocity, like the Earth relative to CMB, 600 miles per second, the Earth will observe blue shifted CMB photon gas, and the other side is red shifted. Then this actually observed the temperature ahead of the Earth's motion is 0.35 millikelvin, and the other side is 0.7 colder. But the pressure of the photon gas is related to this. So if we put 2.2725 plus this, or 2.725 minus this, the temperature difference, plug in, you'll find out the two sides of the Earth has a pressure difference just because the existence of CMB. And if you multiply the pressure with the cross-section of the Earth, you can estimate the force acting on the Earth. It's about this big. That's big, right? Suppose we have a kilogram of mass here holding here, the Earth will attract it, and the force will be 9.8 Newton. But then the CMB acting on our Earth about this much. So for Earth is negligible, nothing. But a photon travel at the speed of light, 300,000 kilograms per second. The drag could be big. Let me demonstrate it. Suppose CMB photon come from every direction toward the center. And then a photon travel here. First, if we put an object sitting still inside the CMB photon gas, the pressure from every direction is the same, so the net force is 0. But if a photon travels this way, all those CMB photons come far, far away, reach here, they are in the same direction of the photon, traveling photon. And on the other side is the opposite. So in a way, this photon will feel more from this photon gas. So that's why I'm suggesting, all right, a photon travel in CMB need to overcome the pressure of the CMB photon gas. Mainly, I'm arguing here because this thing come here, this half of the microwave photon is along the same, has component along the same direction. But this side is just like oppose the microwave. So it experiences a pressure. And the pressure, the force will be equal to the pressure of the microwave background. We know is small quantity, but the pressure. And the cross-section of the photon could be very small. So pressure times the cross-section will give us the force experienced by the light, by that photon. Let's demonstrate this. Let's assume the photon has a peak wavelength, like the visible spectra, lambda equal to 500 nanometer, okay? And the photon gas has this temperature, 2.725, it has a pressure. The energy of photon at that wavelength is this much. The interaction cross-section, let's assume, equal to lambda square. Okay, the photon has a lambda. Lambda square is a cross-section, move against the photon gas. And the photon gas is a known quantity calculated with that temperature is this much. So the force acting on the photon is a cross-section times the pressure is this much. The energy loss per unit is this, so we know the total energy. We know the force. So force times distance will get the energy loss during time travel. It turns out the photon travel 1 second in the photon gas, you will lose all its energy. That's a rough estimate. These slides demonstrate the microwave background photon is relevant. It can be relevant. It's probably is over relevant. Okay, so now let's criticize our assumption. So no, this estimate is too much maybe. And another thing is
Quick comment. This is a basic QED process, photon-photon scattering. You can look up what the cross-section is. It's 2 photons come in. There's a box diagram from an electron. One makes an electron-positron pair. And then they annihilate again to make 2 photons. So it's elastic photon-photon scattering. It's a difficult calculation, but it's well known. You can actually look up in textbooks what that photon-photon cross-section is.
I'm glad you brought it up. Okay, so now this is probably a rough estimate. And this one, like he said, the photon-photon interaction, the Maxwell equations are linear, so they don't interact at first. But higher order interaction, quantum electrodynamics say, yeah, there should be some interaction, but it is involved electron-photon virtual pair. You know, they come up, they disappear. But that's a higher order interaction. Maybe, you know, just now I use the cross-section and the pressure. That's not quite right. But I don't know how to calculate that. In the literature, people calculate 1 electron volt, 1 electron volt cross section. Japanese people calculate like a cross section 10 to the minus 35 in some unit. And earlier classical calculation 10 to the minus 72. That's 1 electron volt, 1 electron volt. It's unsettled. And the calculation involved is like this. Imagine I'm a photon. I travel this direction. I see a photon gas. I'm plowing through this. So if I want to calculate, I need to calculate the photon, me, and a microwave photon coming from different directions. Then calculate cross section, sum them up. I would hope some people would do that. It's a tedious calculation, but you see, the model result can come up with a cross section. That's like experimental result in the universe, big laboratory. So people interested in making that calculation can compare. That can be a very, but I don't. So far, I have not convinced anybody to do that. So now let me just outline a few lines how I do that. See, the energy of a photon change as a function of distance is related to a cross-section time pressure. I added the energy of the photon here. This is my assumption. The reason I made this assumption is like this. If a particle travels in air, the pressure drag proportional to the velocity square of that particle. So I follow that. I put the energy of photon here. And the good thing is the result, I can get a redshift and a distance relation, that's a constant, independent of frequency. That's an observed fact. Big Bang followed that, satisfy that requirement. Okay, now this, I didn't mean to show anything, I just to outline. Another thing is, if I have a beam of light coming to my to an observer, then because of the interaction, the intensity of the beam will reduce. So the observed number of photons and the emitted photon will attenuate. Those are the two things I used in the model. Okay. Oh, sorry. And so then I try to use the definition of distance modulus and so on and so forth. I come up the two equations. So ignore those equations. One result is this. The distance modulus is related to the one constant I use and another constant defined. But now this is an experiment observed mu, this is z. And in the literature, they observed this from supernova or gamma ray bursts. Those are gamma ray bursts, and those are supernova result. One side is a redshift, the other side is a distance modulus. That's the most important observation related to the universe. Any model, you need to explain this. So now here's the result. Yeah?
What does mu represent?
Mu is related to what the starting magnitude, and then the observed magnitude, and that's related to luminous distance. And so here I just outline from my equations I can derive this, the details not there. So now, then this is the experimental observation result. And here's, not many people use the lambda CDM model to calculate. I use a calculator. So I calculate for the Big Bang model on the dashed line. And then my model, the red line. They are equally well. That's the conclusion there. So the main result is the redshift distance relation, okay, and also the distance modulus as a function of z, and this consistent, similar to the Big Bang. This can explain observation. Not too many observations available. And this one, let me show you this. Big Bang says, if this is our cosmic time, here is about 13.8. If you close to the Big Bang time, lambda CDM model says, the z, the redshift, will increase to infinity. But the equation I showed you earlier is like this. For instance, recently, James Webb observed a galaxy with a redshift 16.7. If it's a Big Bang model, it will show, oh yeah, that probably happened about so many million years ago. But if I use the model I mentioned, it could be happened to here, like maybe minus 35 plus 15, about 15 billion years ago. And this, so the point is, if you use Big Bang because of the lifetime or the rapid extension, you need to explain things with those. But now if a static universe, you just explain it a longer time farther away. Now another indication, say, what's the difference I can tell from the model I proposed and the Big Bang? Big Bang model, the universe, the temperature is decreasing. During the recombination microwave, that's 3000 K. But now, currently 2.72 K. Maybe 5 gigayears from now, it dropped to that. So, we will be frozen to that, right? We will, few billion years or something. But the microwave background, the energy in there, it can be produced by all the stars in our observable universe, 31 gigayears. So in other words, the CMB can be produced by the stars in our observable universe, in the observable universe.
Temperature degrading because of the separation.
Because space expansion. Yeah. So in other words, the temperature of the universe keep dropping, and the
separation, further and further separation. Point source 1 over R squared diminished.
No, I'm sorry. This temperature is a temperature of the microwave background, and that we call that the temperature of the universe. If the universe expand, the density decrease, right, the wavelength stretch, and that causes that. So now this just indicates the trend. Now the reason I'm showing this like that, the present model will say the temperature of the universe increase, say, from from the Big Bang, like 13.8 years ago, maybe a little bit over 2 Kelvin, but now increased to, now it's 13 point something, now increased to 2.7, then maybe another 10 years or something, 15 years, is increase that. And so this prediction is different. But who can do an experiment like that? But they are experiments. Some people observe the absorption spectrum of some molecules or nucleus a long time ago. He said, oh yeah, this thing is immersed in microwave background. The microwave background had a temperature then. So now, then they determined the temperature. So maybe say 1 billion years ago, temperature instead of 2.725, maybe 3 or so on and so forth. They are experiments like that. But it's very hard to say something is immersed in microwave background without the influence from other things. Like our James Webb telescope, the one side, and now one side in even no sunlight or something is what 200 some degree Fahrenheit or something. It's very cold. So nearby any source will affect that. I'm sorry.
I understand why the lambda CDM model would have the CMB decreasing in temperature because space is expanding and it's basically the source is getting farther away, so it's getting colder. The wavelength is attenuating, getting colder, frequency is diminishing, right? That makes sense. But in your model, what is the explanation, the theoretical, not the mathematical, but what's the philosophical explanation for your increasing temperature?
Okay, think about this. Earlier view graph I showed the microwave background that we have now, here 410 of them. Microwave background photons here can be generated by all stars in our observable universe within 31 years. If the universe is so old, over, at least 31 giga years, right? So now down the road, start keep emitting, yeah.
You're saying more stars are being produced? They're creating more light?
No. The current star will continue to emit the light.
You mean photons from farther away are reaching us more and more?
Even use my model. If we observe a microwave background photon, it can be from 100 billion light years away, or maybe few billion light, depend on the source wavelength. Instead, Big Bang said, no, all of them came from the same distance, same original photon. That's the difference. But now there's a relevant question. Now, if the universe is infinite and the time is infinite, then by now, the energies we are talking about, the microwave background energy generated, should be a lot. Maybe the temperature should not be 2.7, could be 1,000, who knows? So there might be involved things like this. There's no reason for more material to appear in our universe. But the materials will continue to disappear or to be eaten by black holes or something. Like our black hole in our Milky Way near the center, about the size of the sun. They have 4 million solar mass in there. That's in our very galaxy. And in a galaxy called the M87, 6.5 billion solar mass in a size not too much bigger than our sun. So who knows? There might be material, energy, circle things involved. material disappear and change to other form. That's beyond my capability, but my speculation. Then let me just mention a few other things, very few. Okay, experimental observation. If we use a telescope, look around every direction, we'll observe light. Those light are diffused. I mean, not a discrete size, not this galaxy or something. So some of the gamma rays is just about uniform in every direction. Some of them optical, and some of them infrared and X-ray and so on. They are not in black body distribution. If it's optical in black body distribution, then we'll be all roasted. But the density is the energy contained in microwave is about 30 times bigger than this, or either of the two. So in other words, the electromagnetic energy in the universe mainly contained in the microwave background. But now this one has a black body distribution. Then let's speculate. Why this thing keep going down, the energy keep going down, or microwave. So the concentration keep going up with the longer wavelengths, and the energy keep more going there. So in a way, one speculation would be the light source, like the sun, emit light, Earth absorbs the light, sunlight, re-emitted at 300K, whatever range that. So Pluto absorbs sunlight very little, and is re-emitted maybe, 50K or something. So one process is higher energy photon will transfer to low energy photon. That's very small quantity. Another thing is the model is saying any photon travel in the microwave background will lose the energy gradually, maybe 1,000 giga-years or so, it will lose. All microwave background we see, use the model I just described, come from 100 gigalight years, 50 gigalight years. So in other words, photon due to interaction or due to absorption, emission, will eventually settle down to the lowest energy and the highest entropy. So in that sense, this may not be the relic of Big Bang, it could be a natural result. Then one question people will ask, if you have infinite space, the infinite of stars, how come the sky is not bright, right? You heard this. So then the solution, Big Bang solution, is the age is only 13.8, so not enough time to come, or space expansion will reduce the energy. But in the model I'm talking about, all photons come to us is about 100 some light years. Beyond that, their energy already absorbed by the microwave. So if we can see in the microwave range, the sky is bright all the time. Let me see, I don't know, I have one more thing. Oh yeah, so the Big Bang model calculates the temperature of the universe. It's a log scale. So when time is time equal to minus 45 second, temperature is 10 to the 32 K or something. So it's a very mind-boggling Big Bang model. But the model I'm proposing, maybe earlier time could be 2 degrees, now it's 3 degrees or 4 degrees or something. I think maybe I'd better quit here. Yeah.
So, as I recall, the cosmic microwave background, one of the earliest measurements sort of showed it kind of uniform. And so there was a controversy that if it were really uniform. Yeah, I'm saying if the cosmic background, the earliest measurements showed it being kind of uniform. And if it were uniform, you would have no reason to think galaxies and nebula or galaxies and stars should form out of it. There just should be a uniform expansion. But then as they got better measurements, they saw this structure to it, which went with the fact that there are galaxies and structure in the universe. So what, in your theory, what do you have to say about the structure that's in the cosmic background, microwave?
Yeah, the cosmic microwave background, there are small fluctuations. They say those fluctuations correspond the non-uniform things. Now, Big Bang model use, say, like a quantum vacuum, for instance, with a high temperature. So you went through like a quarks and nucleus, finally hydrogen, helium. They start with small particles, and then they get together, form the galaxy. In the model I'm thinking, the earliest universe, even infinite time, it cannot be with a galaxy like that right there. Probably going through evolution period. Could be started from smaller particle like a hydrogen, for instance, and then gradually combine or.
I could follow up on what John
Sure.
was just saying. I mean, you always look for interesting predictions, like what does an idea predict that you can test experimentally? And in the standard Big Bang cosmology, I remember seeing it was a prediction of the anisotropy, again, of the cosmic microwave background radiation, because they have detailed measurements of the departure from spherical distribution, and they can experimentally extract the higher multiples, not first, second, third, fourth, but up to 100 or so. And they have a very complicated behavior that's oscillatory. And you can calculate this in the standard Big Bang model, and the prediction sits right on top of the data. And now I don't know how many parameters they have. I think it's like 2 or 3 or 4, something like that. But that's really what convinced me as well. I'll bet no other model can do anywhere near as good a job of predicting the higher multiples.
Yeah, you are referring to, if we look at the intensity of a microwave background, there are some uneven part, maybe
The YLM moments,
yeah,
the higher multiples,
and also the deviation of intensity of the order of 10 to minus 5, small deviation. But now think about this. All microwave background photons come from all directions far, far away. They will go through they will interfere to some extent by the existing galaxies, stars. So the unevenness can be produced by those objects during the long trip here. I don't remember the source. I remember some people try to explain that way for infinite universe. In other words, the shadow, the existence of all the galaxies and stars in the microwave photons way, they will cause disturbance. And that is similar to Big Bang distribution of the galaxies. You may get a similar result if you do multiple amplitude analysis.
Which is to be shown, but I'm saying there's a really interesting standard Big Bang model calculation of this that really fits the data well. So you've got a big problem to deal with.
Yeah, but you also have you heard Big Bang has 20 or so parameters?
Model has 20 or so.
20 or so.
That's what I was wondering, is how many of those are really important in getting the anisotropy of the CMB? That I don't know. That'd be an interesting thing to ask some people. I think it's a smallish number of
But I'm not so sure I would treat that as a real observation, really. It's like someone make a theory, then make a story, and then try to fit it. I don't know. I'm not familiar with that. But I vaguely remember I saw some published paper saying the nearby or the existing galaxies, their distribution may cause similar distribution. Yeah, David.
Yeah, I've got 3 comments, if I can remember them. First is that a lot of the older material is now residing in black holes. Once it gets there, we lose the identification of what elements are present, and we don't see those contributions. Second was that as people that are, and we have some people on Zoom, if they have questions, they can type it in the chat, and one of us that are monitoring the chat will relay to you. And the third thing is a question. Do you have any ability from your model to predict the existence of dark matter? That's just a big mystery to me. So-called dark matter. Thanks.
In my model, it eliminates the dark energy because no expansion. We don't need it. Dark matter, I have no idea, but I think it should be something there to explain the observed, like a star orbits or something. A person in Europe, he published a series of papers. His idea is like this. There's such a thing called a quantum vacuum. Inside the quantum vacuum, they are virtual, they are matter and antimatter, they are virtual. Sometimes they polarize, form a dipole. If you have a galaxy here, is a lot of mass in there, then that will polarize the quantum vacuum things, then produce dipole. That dipole interact with the galaxy and the stars in it. I have not followed up there, but the first time I saw that few papers by that person, I think, oh, this is going to solve all my problems down the road. I have not pursued it.
So where does the multiverse theory come into all this?
I have no idea. We even have a hard time to deal with the universe one we have.
Is part of your motivation for this alternative model a result of preference of yours, if such preference exists, for a infinite universe with a preference, like a distaste for the Big Bang model? Is there some preference from you in that regard?
To me, Big Bang is a prevailing model. I cannot say, oh, this is a jungle. We cannot say that. But the the things I present here indicates just how, what's the word, bizarre or abstract, mind-boggling. So in a way, it's so unusual. Let me use that word. But if, down the history, people visualize the universe as static, infinite. Even Einstein, he tried to use his constant to make the universe static. So, but I think from my feeling, I know scientists should not feel, but my feeling is that Big Bang model is so mind-boggling. It's hard to believe. It's incredible. And also, now the new things going to be found. Nobody knows what will happen. Like 200 million years, we'll develop the galaxy.
Thank you so much.
Thank you.
It's a very thought-provoking seminar here, and we'd like to give you a little gift.
Oh, no.
Speakers.
Yeah.